Alright, let's dive straight into the fascinating world of electronic design automation, or EDA, specifically for very large-scale integration, VLSI. Think of it as the digital blueprint for building the incredibly complex chips that power our modern lives. First up, let's get familiar with the workhorse of modern electronics, the MOSFET, metal oxide semiconductor field effect transistor. It's basically the tiny switch that makes everything digital tick. You've got the metal gate, usually polysilicon these days, sitting on top of an insulating oxide layer, typically silicon dioxide, which is the SiO2 part, and then the semiconductor substrate, usually silicon. This simple structure, MOS, allows us to control the flow of current with incredible precision. It's the fundamental building block we're designing circuits around. Now, imagine trying to build a skyscraper without blueprints or simulations. Chaos, right? That's where simulators come in. These are powerful software tools that act like a virtual lab for your circuits. Instead of soldering wires and hoping for the best, you feed your circuit design into a simulator, and it predicts how it will behave. Why is this a big deal? Huge time savings. You can test dozens of designs before even picking up a soldering iron. Massive cost savings. Catching errors early means fewer expensive prototypes. It drastically reduces risk. You spot potential failures before they hit the real world. It's also a fantastic learning tool for students, letting you experiment safely. And crucially, it handles complexity. Simulating a billion transistor chip? No problem, mostly. So, how do these magic boxes actually work? The core idea is modeling. You take your physical circuit and translate it into a mathematical language. Think of it like creating a detailed recipe for your circuit. First, you list all the ingredients: resistors, capacitors, transistors, etc. Then, you write down the rules governing each ingredient: Ohm's law for resistors, the transistor equations, Kirchhoff's laws for how things connect. You assign specific values: how much resistance, how much capacitance. Sometimes, you simplify the recipe to make it easier to cook, or in our case, simulate. It's about capturing the essence of the circuit in a form the computer can understand and crunch numbers on. Okay, so you've built your virtual model. Now what? You perform analysis. This is where the simulator gets to work. You can ask it, what happens when I apply a constant voltage? That's DC analysis. Or, what happens when I feed in a sine wave of different frequencies? That's AC analysis. Maybe you want to see how the circuit reacts over time, like when a signal turns on or off? That's transient analysis. And crucially, you can analyze noise, those pesky random fluctuations that mess with signals. The simulator spits out results, often as graphs and waveforms, making it easy to visualize. Then, you iterate, tweak the design, run the simulation again, and repeat until you're happy. It's a cycle of prediction, testing, and refinement. Not all simulators are created equal. There are different types tailored for different jobs. Let's start with the most common, circuit simulators. These are your general-purpose workhorses. Think SPICE, Multisim, LT-SPICE. They're great for both analog and digital circuits, using detailed models of components like transistors, resistors, and capacitors. Before you spend a fortune on a physical prototype, you use these to predict how your circuit will actually behave. It's like having a crystal ball for your electronics. Next up are digital simulators. If you're working on logic gates, microprocessors, or FPGA designs, these are your go-to tools. They use hardware description languages like Verilog or VHDL, which you write to describe the logic of your digital circuit. Tools like ModelSim or Vivado let you simulate this code, step through it, and debug it, making sure your digital logic actually does what you intended. It's crucial for verifying complex digital systems before you even think about laying down silicon. Once your logic design is solid, you need to lay it out physically. That's where layout simulators come in. Tools like Cadence Virtuoso or Synopsys IC Compiler don't just simulate the logic. They check if your physical layout follows the strict manufacturing rules. Think of it as checking if your building plans meet zoning laws and structural requirements. They ensure features are wide enough, spaced correctly, and properly connected, preventing nasty surprises during fabrication. It's about ensuring manufacturability. Then we have device simulators. These are deeper dives, focusing on the semiconductor device itself. Tools like Silvaco Atlas or Synopsys Centaurus TCAD allow you to model the physics inside a transistor, predicting its behavior based on doping levels, temperatures, and electric fields. This is crucial for designing new types of transistors or optimizing existing ones for better performance or lower power. It's like understanding the engine's combustion process, not just driving the car. The list goes on. Electromagnetic simulators like HFSS or CST Microwave Studio are vital for high-frequency RF and microwave circuits, analyzing electromagnetic waves and radiation. Thermal simulators like ANSYS IcePack help manage heat, which is a huge concern in dense integrated circuits. Power electronics simulators like PSIM or Plex are specialized for circuits dealing with high voltages and currents. FPGA simulators like Vivado or Quartus Prime are dedicated to simulating field-programmable gate arrays. And finally, mixed signal simulators bridge the gap between analog and digital, handling designs that have both types of components. Each type has its niche, but they all serve the same goal: predict and optimize electronic behavior virtually. Here's a typical workflow you might see in practice. You start with a schematic, a drawing of your circuit. Then you use a simulator like T-Spice to analyze its behavior. Next, you create the physical layout using tools like L-Edit. Crucially, you verify this layout against design rules using tools like Hyper-Verify. Often, you'll run simulations after the layout is done, post-layout simulation to account for parasitic effects introduced by the physical implementation. Finally, once everything checks out, you generate the masks for manufacturing tape-out. It's a complex dance, but simulation is woven throughout. Let's take a quick trip down memory lane. Circuit simulation didn't just pop up overnight. It started gaining traction in the late 60s and early 70s. But the real explosion happened in the 70s with the rise of integrated circuits. Suddenly, building a chip was super expensive, and debugging was a nightmare. You couldn't just tweak a resistor, you'd have to send the whole chip back to the fab. This is where simulation became absolutely essential. Two key players emerged. IBM's ASTAP group developed the numerical methods, and the SPICE group at Berkeley, initially a student project, created the standard simulator. SPICE, written by Larry Nagel, became the de facto industry benchmark. Why did SPICE become so dominant? 3 key reasons. First, it was explicitly designed for integrated circuits. Unlike earlier tools, SPICE had the necessary models built right in. Second, Berkeley made the source code available for a small fee, allowing widespread adoption. Third, Berkeley grads carried SPICE knowledge to companies everywhere. For a while, everyone had their own internal version of SPICE, seeing it as a strategic advantage. But then, commercial simulators started getting better, faster, and cheaper. By the late 80s and 90s, the tide turned. Companies realized they could buy better commercial tools than maintain their own, and now, only the biggest players still develop their own proprietary simulators. The era of universal SPICE dominance gave way to a diverse market of commercial solutions. Berkeley didn't stop there. In the late 80s, they released SPICE 3, which was a major upgrade, written in C, making it easier to add new models. Around the same time, they developed Spectre. This was different. It used harmonic balance, a clever technique to directly find the steady-state solution for nonlinear circuits, especially useful for microwave frequencies. HP picked up Spectre, renamed it MNS, and Cadence later adapted its algorithms. So, while SPICE evolved, new approaches emerged, pushing the boundaries of what simulation could do. Let's peek under the hood at a typical component model. Here's a snippet from a ROHM MOSFET model. It's basically a list of parameters that define the transistor's behavior. Level equals 3 tells you it's using a specific model type. L, W, KP, VTO, TOX, CGSO, CGDO, and so on. These are all physical characteristics and electrical properties. RS, RD, RB, gamma, ETA, kappa, NFS. These are model parameters that fine-tune the behavior. It's a complex set of equations, often derived from physics, that the simulator uses to calculate the transistor's response. The formula is shown here. K equals 1/2 mu COX times W over L, and VT equals VT0 plus gamma times the square root of 2 phi F plus VSB minus the square root of 2 phi F are just parts of the bigger picture, describing transconductance and threshold voltage. Okay, let's talk about DC analysis. This is fundamental. It calculates the steady-state operating point of your circuit, assuming all input signals are constant. But sometimes, you want to see how the circuit behaves as you change a DC source, like sweeping the input voltage. That's where the DC sweep analysis comes in. Controlled by a .dc statement, it essentially runs multiple .op analyses automatically. You tell it which source to vary, the starting value, the increment, and the final value. It's like asking, what happens if I slowly increase this voltage from 0 to 10 volts? This is super useful for characterizing amplifiers, diodes, or any circuit whose behavior depends on DC levels. Why is DC sweep faster than just running .op multiple times manually? Well, PSpice doesn't have to read the entire circuit file and solve the whole system from scratch each time. More importantly, it's smart. It assumes that the solution for the next source value is close to the previous one. So, it takes the solution from the first calculation, uses it as a starting guess for the second, and so on. It even uses extrapolation, looking at the last two solutions to predict the next one. This iterative approach, leveraging previous results, makes the sweep process much more efficient than solving the full circuit independently at each step. How do you actually tell PSpice to do a DC sweep? With the .dc statement. It's straightforward. .dc source name, start value, stop value, increment value. You specify the name of the independent source you want to sweep, the starting voltage or current, the ending value, and how much you want to increase it by in each step. For example, .dc VON 010 0.1 would sweep the voltage source VON from 0 to 10 volts in steps of 0.1 volts. Remember, this statement only overrides the fixed value you set for that source in your circuit definition. If you forget to define the source, the .dc statement won't work. After running a DC sweep, you probably want to see the results. The print DC statement is your friend here. It lets you specify exactly what you want to print out. You can print node voltages, like V7, for the voltage at node 7, or the difference between two nodes, V6, 3, for V6 minus V3. You can also print device currents, like RON, for the current through resistor RON. You can even print multiple values together, like print DC, V4, RA2, and PSpice will neatly organize them in a table. It's all about controlling what data you extract from your simulation. Looking at tables of numbers can get tedious, especially with many sweep points. Thankfully, PSpice has the plot DC statement. It works just like print DC, but instead of a table, it generates a graph. You can plot node voltages, currents, or combinations thereof. And you can even control the axis ranges, like plot DC, V, 3, 0, 10, to zoom in on specific regions of interest. This visual representation makes it much easier to understand trends and relationships in your circuit's behavior as you sweep the DC source. It's like going from a spreadsheet to a chart. For a more interactive experience, PSpice offers Probe. This is a graphical waveform viewer. To use it, you first need to tell PSpice to save the data for Probe using the .probe statement. You can then specify which outputs to save, similar to .print or .plot. The beauty of .probe is that it saves all the data points for all the specified outputs. Later, you can open the probe window, select any waveform you saved, and view it interactively. You can zoom, pan, measure values, and explore different parts of your circuit's behavior without rerunning the simulation. It's like having a persistent oscilloscope for your simulation data. Imagine you've designed a really neat little function block, like a square root calculator. You'd hate to have to redraw it every time you wanted to use it in your main circuit. That's where subcircuits come in. It's like creating a reusable macro or module. You define your subcircuit once, giving it a name, and specifying which terminals connect to the outside world. Then, you can use this subcircuit multiple times in your main design, just like using a pre-built component. The syntax is .subct definition name node 1 node 2 ... followed by the components inside the subcircuit, and then .ends. When you define a subcircuit, you list the nodes that are its external connections. Inside the subcircuit definition, the node numbers are local to that block. The example here defines a subcircuit called scroot with 4 terminals, 1, 2, 3, and 4. Nodes 1 and 2 are inputs, and 3 and 4 are outputs. The internal components like FW, AREV, REV are defined within this block. Notice how the input nodes 1 and 2 and output nodes 3 and 4 are left floating in the sense that they are not connected to anything else within the subcircuit definition itself. They are just placeholders for connection points. So how do you actually use this subcircuit? You use a special component type that starts with an X. The syntax is xname nodion node 2. Subcircuit, definition, name. You must use the exact same order of terminal nodes as you defined in the subct block. In the example, xblock 1020 SQ root connects the external circuit's node 1 to the subcircuit's input node 1 and node 0, ground, to the subcircuit's input node 2. Similarly, it connects the subcircuit's output node 3 to the external node 2 and output node 4 to external node 0. The subcircuit definition is placed somewhere between the title line and the end statement. You can even put these definitions in separate library files and load them using the lib command. To keep things organized, especially when you have many subcircuits, you can store them in library files. These are like toolkits of reusable functions. You can create a file containing several subct definitions, and then, in your main circuit file, you simply use the lib command followed by the file name. PSpice will then know where to find those subcircuits when you use them with the X statement. This makes managing complex designs with many repeated blocks much cleaner and more efficient. It's all about code reuse and organization. Moving on to AC analysis. This is incredibly popular for analyzing filters and control circuits. The goal is to see how the circuit responds to sinusoidal inputs across a range of frequencies. Think of it as sweeping the frequency of a sine wave generator and measuring the output. The key output here is the frequency response, which includes the amplitude and phase shift of the output signal relative to the input at each frequency. It's important to note that this is typically small signal analysis, meaning the input signals are assumed to be small enough that the circuit's behavior stays linear. Don't confuse this with transient analysis, which looks at time-varying responses, even if they are periodic. Let's look at a simple example, a common emitter amplifier. We can use AC analysis to find its frequency response. The circuit diagram shows the setup. The characteristic curves show the DC operating point, the Q point, determined by the biasing resistors RB and RC. The formulas calculate the DC bias current IBQ, collector current ICQ, and collector emitter voltage VCEQ. Now, If we apply a small AC signal at the input, the output will be amplified, but its amplitude will depend on the frequency. AC analysis helps us determine the gain and phase shift across the frequency spectrum. These diagrams illustrate the importance of the Q point. If the Q point is too close to saturation, like in Figure A, a small input signal might push the transistor into saturation, causing distortion. Similarly, if the Q point is too close to cutoff, like in Figure B, the signal might clip at the bottom. Ideally, as shown in Figure C, the Q point should be centered in the active region, allowing the input signal to swing symmetrically without hitting the saturation or cutoff regions. AC analysis helps us understand the gain and phase shift, but it assumes the signal is small enough to stay within the linear region. Large signals can cause nonlinear effects, which AC analysis doesn't capture directly. To perform an AC analysis, you use the .AC statement. This tells PSpice the frequency range and type of sweep. You can choose between linear, octave, or decade sweeps. For a linear sweep, you specify the number of points, the start frequency, and the end frequency. For example, .AC lin 100 100 Hz 10 kHz would sweep 100 points from 100 Hz to 10 kHz in a straight line. This is useful for narrow frequency ranges. The syntax is similar for other sweep types. For wider frequency ranges, especially common in RF and audio, logarithmic sweeps are often preferred. An octave sweep, .AC-OCT, divides the frequency range into intervals where each interval is twice the frequency of the previous one. You specify the number of points per octave. A decade sweep, .AC-DEC, does the same but for intervals 10 times the frequency. Again, you specify the number of points per decade. These logarithmic sweeps are much more efficient for covering large frequency spans, like from 10 Hz to 100 MHz, because they concentrate more points where the frequency changes rapidly. Just like with DC analysis, you can use print-ACK or plot-ACK statements to get the results of your AC analysis. You can print the magnitude of the voltage at a node, like V7, the phase of the voltage at a node, VP7, the real part of the current through a device, IR, RON, or the imaginary part, I, RON. You can combine these, like print ACV, 3, VP, 4, 2, and PSpice will organize the results by frequency. The output will be a table or a plot, showing how these quantities change as the frequency sweeps. A very common way to visualize AC analysis results is the Bode plot. It's a pair of graphs, one showing the magnitude of the gain or impedance versus frequency, usually in decibels, and the other showing the phase shift versus frequency. The top graph shows the magnitude plot, gain in dB versus frequency on a log scale. The bottom graph shows the phase plot, phase in degrees versus frequency on a log scale. This combination gives you a complete picture of the frequency response. The RC low-pass filter example on the right shows how the gain drops off and the phase shifts as frequency increases. Let's apply this to a real filter circuit. This is a double-pole, low-pass LC filter. We've split the input resistance into sections, each forming a parallel resonant circuit with an inductor and capacitor. The goal is to see how the filter shapes the frequency response. We'll use AC analysis to find the magnitude and phase response. The circuit diagram shows the components and the different Q values for each section. The values are chosen for an audio frequency range. Here's the circuit description for the simulator. We have the input source VIN, and then 4 identical filter sections, each with a resistor R, inductor L, and capacitor C. The comments indicate the Q value for each section. The .AC-DEC 100 100 Hz 10 Hz statement sets up a decade sweep from 100 Hz to 10 kHz with 100 points. The .probe statement ensures the data is saved for viewing in probe. The .end statement marks the end of the circuit description. Let's run this simulation and see what probe gives us. And here's the magnitude response from probe. We plotted the output voltage at nodes 3, 5, 7, and 9, which correspond to the outputs of the sections with Q equals 0.5, 1, 2, and 4, respectively. As you can see, the filter with the highest Q equals 4, Vm, 9, has a sharper peak near its resonant frequency. The lower Q values, Vm, 3, Vm, 5, Vm, 7, show broader peaks. This demonstrates how the Q factor affects the selectivity of the filter. Higher Q means a more selective filter, but it can also be more sensitive to component variations. Now let's look at the phase response. Again, we plotted the phase at nodes 3, 5, 7, and 9. Notice how the phase starts near 0 at low frequencies and shifts towards -90 degrees as the frequency increases, especially around the resonant frequencies. The phase shift indicates the delay introduced by the filter. For a low-pass filter, the phase shift is typically negative, meaning the output lags behind the input. The amount of phase shift is crucial for understanding signal integrity, especially in cascaded systems. Phase response is closely related to another important concept, group delay. Think of a signal as a collection of different frequencies. If the phase shift is linear with frequency, the delay is uniform, and the signal shape is preserved. But if the phase shift is non-linear, different frequencies get delayed by different amounts, causing the signal shape to distort. Group delay is defined as the negative derivative of the phase with respect to frequency. It represents the delay experienced by a group of frequencies, like the envelope of a modulated signal. Flat group delay is desirable for maintaining signal integrity. Probe can calculate group delay directly from the phase data. Here we plot the group delay for the same filter sections. The group delay shows how the delay changes with frequency. Ideally, you'd want a flat group delay. Notice how the group delay spikes near the resonant frequencies of the filters. This is because the phase is changing rapidly there, leading to large variations in delay. High group delay variations can cause significant signal distortion. Comparing these plots helps you understand the trade-offs between different filter designs. Another key parameter is input impedance. How does the input impedance of our filter change with frequency? We can calculate this using the simulation data. Impedance Z is the ratio of complex voltage V to complex current I. Using complex numbers, we can express the magnitude and phase of the impedance. The magnitude of the input impedance is the magnitude of the output voltage divided by the magnitude of the input current. The phase of the input impedance is the phase of the output voltage minus the phase of the input current. Using the LC filter circuit again, we can plot the input impedance without rerunning the simulation. Since we already calculated the output voltage and input current, we can simply divide them. For example, V divided by IR gives the magnitude of the input impedance for the first section, Q equals 0.5. V divided by IR for the second, Q equals E, and so on. This allows us to see how the input impedance varies with frequency for each filter section. Understanding input impedance is crucial for matching stages in a larger system to maximize power transfer and minimize reflections. Now, let's switch gears to noise. Noise is everywhere in electronics. It's the unwanted, random fluctuation in electrical signals caused by the inherent randomness of atomic processes. Think of it as the static on a radio, or the grainy texture in a blurry image. It's not related to the input signal itself, it's just there. The diagrams show a clean signal versus a noisy signal. Noise can corrupt the desired signal, making it harder to detect or process. It's a fundamental challenge in electronic design. Noise analysis helps us quantify and understand this noise. It's crucial in communication systems, audio equipment, sensors, and anywhere sensitive signals are processed. The diagram illustrates how noise can be introduced into a signal path, degrading the quality of the received signal. The goal of noise analysis is to predict the noise level in a circuit, allowing designers to mitigate its effects. It involves calculating the contributions of various noise sources within the circuit and combining them. Noise can be broadly categorized into internal and external sources. External noise comes from outside the circuit, like atmospheric noise, man-made noise, or interference from other devices. Internal noise originates within the circuit components themselves. The most common types of internal noise are shot noise and thermal noise. Shot noise is due to the random arrival of charge carriers, like electrons or holes, in devices like diodes or transistors. Thermal noise, also known as Johnson-Nyquist noise, arises from the random motion of charge carriers and conductors due to temperature. There's also cross-modulation, where signals interfere with each other. Let's focus on the two main internal noise sources. Shot noise is like the random popping of popcorn kernels. It's caused by the discrete nature of charge carriers. When current flows through a device, the arrival of individual electrons or holes is random, leading to fluctuations in the current. Thermal noise, or Johnson-Nyquist noise, is more like the random jiggling of molecules in hot water. Electrons in a conductor are constantly moving randomly due to thermal energy. This random motion creates tiny fluctuations in the current and voltage, which we perceive as noise. The diagram shows a resistor generating this thermal noise voltage. It's present in any conductor at any temperature above absolute zero. When you try to amplify a very small signal, you eventually hit a limit imposed by the noise floor of your equipment. This noise is often called white noise because it contains equal power across all frequencies, like white light contains all colors. In PSpice, you can perform a noise analysis. It calculates the total noise contribution from all components in the circuit and combines them. You can then plot the noise spectral density, which shows the noise power per unit bandwidth as a function of frequency. Resistors in PSpice are modeled as generating an equivalent thermal noise current in parallel with them. To perform a noise analysis in PSpice, you use the dot noise statement. It needs to know which output node you're interested in, which independent source you're considering as the input, and optionally, the interval value for the frequency sweep. Importantly, you must also include a .ac statement to define the frequency range for the noise calculation. The dot noise statement calculates the output noise voltage at the specified node, and the input noise referred to the input source. This allows you to compare the noise level at the output to the noise level at the input. Similar to AC analysis, you can use print noise or plot noise to get the results of the noise analysis. The predefined output values are O noise for the total output noise voltage, I noise for the output noise referred to the input source, dB O noise for the output noise in decibels, and dB I noise for the input referred noise in decibels. These values are typically plotted against frequency. The output will show how the noise spectral density changes with frequency, helping you identify dominant noise sources and frequency ranges where noise is particularly problematic. A key metric derived from noise analysis is the signal-to-noise ratio, or SNR. This is simply the ratio of the desired signal power to the noise power. A higher SNR means a clearer signal, less corrupted by noise. Think of it as the contrast between the picture and the static on an old TV. High SNR is great for clear communication, accurate measurements, and good audio quality. Low SNR means the signal is buried in the noise, making it difficult to distinguish. The diagrams show the difference. High SNR on the left, low SNR on the right. Mathematically, SNR is often expressed in decibels, dB, as 10 times the logarithm base 10 of the signal power divided by the noise power. The formula is S divided by N ratio equals 10 times log base 10 of P sub S divided by P sub N, where P sub S is the signal power and P sub N is the noise power. Remember, the noise level is generally independent of the signal strength. So, if the signal gets very small, the relative impact of the noise becomes much larger, and the SNR decreases significantly. Audio manufacturers often boast about high SNR ratings for their equipment. Typical SNR values range from 10 dB for very noisy systems to 90 dB or more for high-quality audio or communication systems. How do we actually model noise sources in a circuit? For a voltage amplifier like an op-amp, the input voltage noise is treated as a voltage source in series with the input. The input current noise is treated as a current source in parallel with the input. The effect of the current noise depends on the input impedance. If the input impedance is low, the current noise converts to a small voltage noise. If the input impedance is high, like with a microphone, the current noise becomes a significant voltage noise. The diagram shows these two noise sources, E sub n and I sub n, connected to the input of an ideal amplifier. The RMS values of these noise sources are given by formulas involving Boltzmann's constant K, temperature T, bandwidth B, and resistance R. For thermal noise voltage, Vn equals the square root of 4kTRB. For thermal noise current, In equals the square root of 4kTB divided by R. These formulas tell us that noise increases with temperature and bandwidth, and decreases with resistance. To simulate a specific noise level, we can use these formulas to calculate the required resistance. For example, if we want a certain noise current, we can calculate the resistance needed. We can then model this resistor in the circuit and use controlled sources like F devices to inject the calculated noise current into the circuit. Let's walk through an example. Suppose we want to generate a noise current of 10 picoamps per square root of hertz. We know the desired noise current, N equals 10 Pa per square root of hertz, and we want to find the resistance R needed at room temperature, T equals 300 Kelvin. Rearranging the formula N equals the square root of 4kTB divided by R, we solve for R. Plugging in the values, we find R approximately equals 20 kiloohms. So, we create a resistor of 20 kiloohms in the circuit. We connect it across a 0-volt source. Then, we use an F device, a transconductance amplifier, to take the current flowing through the resistor, which is our noise current, and multiply it by a gain factor, say 10, to get the desired noise level. The circuit snippet shows this setup. Now we move to transient analysis. This is arguably the most versatile and commonly used analysis type. It simulates the circuit's behavior over time, showing how voltages and currents change dynamically. This is crucial for understanding circuits with capacitors and inductors, circuits responding to pulses, or even oscillators. However, it's also the most computationally intensive and tricky. The simulator needs to take tiny time steps to accurately capture rapid changes, which can make simulations run very long. If the time steps are too large, you might miss important details or get inaccurate results. It's a balancing act between accuracy and simulation speed. How does transient simulation work? It's based on numerical integration. The simulator predicts the future state of the circuit based on its current state. It assumes that the circuit doesn't change drastically between the current time step and the next one. If the currents and voltages are changing slowly, the simulator can take larger time steps. But if there's a rapid change, like a capacitor charging quickly, it needs to take much smaller steps to capture the dynamics accurately. The accuracy depends heavily on the size of these time steps. The simulator tries to adaptively adjust the step size to balance accuracy and efficiency. When you define a voltage or current source in PSpice, you can specify its behavior for different analyses. The basic syntax is name node, node value. But you can add more detail. Name node, node, DC value, AC value, transient value. The DC value is used for DC operating point and DC sweep analyses. The AC value is used for AC analysis. The transient value specifies the waveform for the transient analysis. If you don't specify a transient value, the source defaults to its DC value and is assumed constant during the transient simulation. This allows you to define complex waveforms for your inputs. The transient value can be a waveform description. Common forms include EXP for exponential waveforms, pulse for repeating pulses, PWL for piecewise linear waveforms, SFFM for frequency modulated signals, and SIN for sine waves. The EXP form creates a waveform that starts at VON, then exponentially rises or falls to V2, and then exponentially rises or falls back to VON. The pulse form creates a repeating pulse train with specified rise time.tr, fall time.tf, pulse width PW, and period per. The PWL form lets you define a custom waveform by specifying a series of time voltage pairs. The diagrams show examples of these waveforms. Continuing with waveform types, the SFFM form generates a sine wave whose frequency is modulated by another sine wave. The parameters define the carrier frequency, the modulation frequency, the amplitude of the carrier, and the amplitude of the modulation. The diagram shows a frequency-modulated sine wave. The pulse form, as mentioned, creates a repeating pulse. The parameters define the initial delay Td, the rise time Tr, the pulse width Pw, and the period per. The diagram shows a typical pulse waveform. The PWL form is very flexible. You provide a list of time voltage pairs, and the simulator connects them with straight lines. The diagram shows an example of a piecewise linear waveform. To run a transient analysis, you use the .trans statement. The basic syntax is .tran/op print interval final time. The final time is mandatory. It tells the simulator how long to simulate. The print interval is optional. It specifies how often the results should be printed or saved. The /op option is also optional. It tells PSpice to print the initial operating point voltages before the transient simulation begins. This is useful if you've set initial conditions that might affect the starting point. You can also add optional parameters like no print interval to skip printing results during the simulation, and step ceiling to limit the maximum time step size. Often, you need to set specific initial conditions for your simulation. Maybe you want a capacitor to start charged to a certain voltage, or an inductor to have a specific current. The .ic statement does this. You list the nodes you want to set and their desired voltages, like .ic vnode equals WV, vnode equals LingV. These are only effective for transient analysis. During the initial bias point calculation, PSpice temporarily connects tiny voltage sources to enforce these values, then removes them before the transient simulation starts. This ensures the simulation begins from the state you specify. Besides setting node voltages, you can also set initial conditions directly on components. For capacitors, you add IC equals initial value to the capacitor statement. For inductors, you add IC equals initial value. This sets the initial voltage across the capacitor, or the initial current through the inductor. Another related statement is .nodeset. It's similar to .ic, but instead of forcing the voltage, it provides an initial guess for the bias point calculation. This can help the simulator converge faster, especially for complex circuits. It doesn't guarantee the voltage, but it guides the iterative process. Let's shift gears to scaling. As we pack more and more transistors onto chips, we need to make them smaller. This systematic reduction in transistor dimensions is called scaling. The goal is to increase integration density while maintaining or improving performance. There are two main philosophies for scaling: constant field scaling, also known as full scaling, and constant voltage scaling. Both aim to reduce the physical size of the transistor, but they differ in how they handle the voltages and doping concentrations. Scaling involves dividing all the horizontal and vertical dimensions of a